Hi everyone, my name is Olivia, and today I'm here with Daniel, Dwani, and also Jimmy. So four of us are all from the Carnegie Mellon University Information Networking Institute, and we are the contributor to Challenge 6. And so today we want to walk everyone through how we contribute to this challenge. And so we'll first start with the initiative background. So the Rust Standard Library contains approximately 35,000 functions, and actually 7,500 of them are marked as unsafe. And this series of challenges is then to focus on verifying the memory safety and a subset of undefined behaviors in the Rust Standard Library. And this initiative is actually a collaboration between AWS and the Rust Foundation. And all the challenges are tool agnostic. So for the four of us, the specific challenge we're tackling is number 6, verifying the null module, which includes 48 public functions. And our goal is to prove the mainly two categories of things. One is the safety requirements that are commented in the source code itself. And the second is proving the absence of four types of undefined behaviors as shown here on the slides. And of course, in the verification process, if we find any actual violations of the above two, then we will also report that to the Rust community. And so our approach, to briefly summarize, is that mainly what we do is first to annotate contracts, especially specifications with pre and post conditions. And on top of that, we generated verification harnesses in the exact same API file attached at the end. And the tool that we chose for this challenge is Connie, which is the open source formal verification tool developed by AWS. And throughout this whole challenge process, we also worked very closely with AWS, including raising questions in the GitHub issue tracker and also the GitHub discussion. So the general rules of thumbs of writing contracts and harnesses that we want to capture on a high level here is that if the function is marked safe, then there will generally be no precondition required in the contract, meaning there's no assumptions needed. However, I also want to mention that for post-condition, which are the insurance clause, these are also assertions that are after executing the function. So the pre and post conditions, if you look at the actual annotations we wrote, will be translated into requires and ensures clauses. And also to the other rules of thumb that we attempt to cover as many data types as possible. So that includes all the integer types, the dynamic traits, slice, composite types, and also the unit type. So for our non-null module, it's mainly broken down into 6 categories of APIs. And then our members right now will walk us through all the individual APIs and how we wrote the contracts and harnesses. So we'll first start with the pointer creation and initialization APIs. So the first two we want to focus on is relatively simpler. They are the new and new unchecked, which just initializes the non-null pointer. And for the contracts, there are two things we want to ensure. One is that the nullity matches the pointer nullity that's being passed in. And then also that the other second thing is that if the result is null, that the pointer in the result is also the same as the pointer that's passed in. And then for the harnesses, it's also pretty simple, is that we just initialize the pointer to a non-deterministic value, and then also execute and call the new unchecked functions, like the one that's shown below. And so for the next one is the dangling function. So dangling function mainly just ensures, we want to ensure that the resulted pointer is non-null and also aligned. And then for the harnesses, we try to create as many data types as possible by calling the function on the different types. So the next ones are the from raw parts and slice from raw parts. So these two functions take in the data and also length and form a kind of a complete object, null pointer. And so for this one, we want to ensure that the result pointer is null, and also that pointer and length also preserved. And then for the harnesses, our approach is that we create a non-deterministic array of an integer type and its size, and then we get a raw non-null pointer to the start of the slice and call a target function with the pointer and the length of slice. We also had added an example for zero-length dangling pointer as well, plus the trait object example, especially for the from raw parts API. And then the other special thing to pay attention to is that for these two, we need to specify the unwind bound in the harness. so that Connie will not try to unwind it indefinitely. And then last thing is the two raw parts. So for this one, we want to ensure the result pointer is non-null and the pointer value is preserved. And to verify this one, we actually created an example trait, um, like the one that's shown here, and then to call the target function with it. And so the next category are the pointer arithmetic and address manipulation. So these six are in that same family. And the difference between the ones without byte and the byte is that the count constraint is different. And so for the contracts, one important thing is to make sure that the count actually conforms to the safety requirements. And then also the second one to ensure that the add and sub operation will result in the same address as offset. And so for harness, here what we did is create a pointer to a non-deterministic address with a fixed size array. And here we actually leverages one of the Connie API, which is the pointer generator, to help us achieve this, which is also shown as in the example here. So we will call the target function on the pointer with this non-deterministic count. And since we already specified the constraints in the required clause, it will help us to make the assumption that the count is a valid count.
So the next three functions in the pointer arithmetic and address manipulation are address, map address, and with address. All the three of these belong to the strict provenance and have a post condition only. When it comes to address, so address is basically gets the address portion of the pointer, and we need to ensure that the return address is equal to the address of the current pointer. The next is map address, which creates a new pointer by mapping self's address to the new one. And for the ensures clause, we need to ensure that the resultant pointer is non-null, which is similar for with address, where also we need to ensure that the resultant pointer needs to be non-null. And the harness for address is straightforward, where we create a non-null pointer and it gets and then we call the address function. But for map address and with address, it's quite similar. We initialize an array and we create a pointer from it using Carney any, and then we generate a new offset, and then we call the function map address or with address according to the harness.
Okay, then I will introduce the APIs about the pointer arithmetic and address manipulation. So the first API, align offset, ensure the pointer has satisfied all the alignment requirements, and offset from computes the distance between the two pointers. Then the third API, subpointers, perform the subtractions between the two pointers. And then I will talk about the contract about these APIs. So the first thing we want to focus is the pointer alignment. We will guarantee the alignment for proper offset computation. And the second is the same allocation. We will verify the pointer are within the same memory allocation area. And the third is about the safe arithmetic. We will ensure the address arithmetic respect the boundaries and module construction constraints. And then we'll talk about the harness procedures. The first we would do is the pointer initialization. We use Connie any or pointer generator to create a valid pointer. And second is the function invocation, like we will call the target function, like the align offset or offset from on non-known pointer modules. And after these API got caught, our contract will be checked to whether they are satisfied the requirement and ensure there's not undefined behaviors.
Next are the pointer casting and type conversion APIs. This consists of four functions: as pointer, as mute pointer, as non-null pointer, and cast. As pointer and as mute pointer returns a raw value to the slices buffer, and cast basically casts a pointer to another type. Harness of and all these four have a similar contract where we need to ensure that the resulting pointer retains the original address. And harness of as pointer and cast is similar, where we create a pointer of non-null value and we call the functions. For as mute pointer and as non-null pointer, we need to ensure that there is a slice that's created from an array. Here I've taken an arbitrary size 100, but that could be any size. And then we call the functions as mute pointer or as non-null pointer to verify it.
Yeah, then I would like to talk about the APIs about pointer to reference conversion. So for this API, the as mutable and as reference can safely convert pointer to a mutable or immutable reference. And as uninitial mutable and as uninitial reference provide access to the uninitialized memory for mutable and immutable operations. And then the as uninitial slice and uninitial slice mutable handle the uninitialized slice of the memory. And the last one, the get unchecked mutable, allow the unchecked mutable access for the memory regions. For this API, our contract memory focusing on three things. The first is the memory access guarantees. We will ensure that memory read and write satisfy the initialization and validation requirements. And the second is the boundary check. We will verify the pointer or slice operation would not exceed allocate memory regions. And the third is alignment validation. We will confirm that the pointer meet alignment construct before the reference conversion. And for this API, the hardness process will be still the first will be the pointer initialization. We will create a symbolic non-num pointers or raw pointers to use Kani any. And the second is pretty similar is the API invocation. We'll call the target APIs with the initialized pointers, ensuring the preconditions are satisfied. And after this contract are triggers, we will what difference here is that we will also focus on some edge cases for invalid offsets, online memory, and out of boundary check during the process.
Next is the memory operations. We have divided these into three categories of APIs: copy, read, and write. I'll discuss the copy APIs. Here it consists of four: copy to, copy from, copy to non-overlapping, and copy from non-overlapping. What differentiates copy to from its non-overlapping counterpart is that in copy to function, the source and destination is allowed to overlap. All these four follow the safety requirements of pointer copy, and it has defined four safety requirements, which are defined in the ensures clause, that the source must be valid for the read of count source of T and must remain valid while the destination is getting returned. It's same while destination is getting returned, the source must be valid for the read. And both the source and destination pointer must be properly aligned. An additional contract is added for copy to non-overlapping and copy from non-overlapping to ensure that the pointers that we have is actually non-overlapping. For harness, it follows a similar pattern for all four. First, we generate an arbitrary non-null pointer. Then we'll create a source and destination pointer using the pointer generator API. And finally, we'll have a max count where we define the size, and then we'll call the unsafe functions and we'll apply that.
And then for the read ones, they're basically reading the value off of specific addresses that the pointer is pointing to. So the first two are read and read volatile. So for these two, the requirements is that the pointer points to a valid value type T. And here we actually use, again, one of the Kani APIs called Candy Reference, which checks that the pointer is aligned, initialized, and also inbound. And for the harnesses, then the approach is to create a non-null pointer of an integer type and then just call the target function on it to read the value. And the second example is to create a non-null pointer to a non-deterministic address in a fixed size array and then call the target function. Again, this is also used using the pointer generator API from Kani. So the read unalign is a little extra and a little special. So this one, the Kani API we use in the required clause is the can read unalign. And then for the harnesses here, because we are checking unaligned addresses, so we used pointer generator again, which it actually covers cases where pointer is potentially unaligned. And also here we added another example of reading from unaligned value from a packed struct, which is also shown in an example from the official Rust documentation.
Okay, so now I'm going to talk about the four write APIs that we contribute. The first one, the write, it writes a value to the location pointed to. And write bytes, it basically just means that it writes a specified number of bytes count of the value into memory. And thirdly, we have write on a line. It handles like writing to online memory locations. Lastly, we have the write volatile. It ensures each write occurs without being optimized away, which is critical for hardware interactions. So for verification, the contract requires that the pointer is writable using UB checks can write. And in the harness, we use pointer generator to create a fixed size memory block and generate non-null pointers within the allocated range. A macro to verify the behavior of write volatile across different data types, including I8, I16, I32, I64, and etc. And also we have implemented the zero size type. And this ensured that the write volatile method worked consistently regardless of the type used. The focus was primarily on write volatile due to some internal Kani limitations with the other write APIs. In the process, we identified and reported a bug affecting the other three write APIs: write, write bytes, write online. This helped contribute to improving the Kani's overall stability.
And then I will talk about the rest of the API that belongs to memory operation types. These three APIs host different functionalities, but they share the similar contract and safety requirements. And the first is the replace. We can replace the value at the pointer's location with a new one value. But also returning the old value without invoking this constructor. And the swap exchange the values at the two pointers, and the dropping place will execute a destructor for the value pointed to, but without deallocating the memory. So for their contract, they have some similar features. So what we want to ensure is the first is the read validity. It will ensure the pointer is properly aligned, initialized, and safe for dereference. And the second is the write validity. It will verify the pointer is valid for writing, at the same time avoid the undefined behaviors. And for the harness process, the first and second step is still the pointer initialization and API invocation. And during the process, he will trigger the function contract to make sure ensure the safety comments. But one thing special here is like, as the example indicates, we also need to use the observed testing to validate the APIs produce the expected outcome, like whether the value are swapped, whether the old value are replaced correctly to ensure the correctness of the API.
Next, I'm going to talk about the alignment and size checks for non-null pointers. So the first one is align. This function checks whether the pointer is aligned correctly for the type it points to. Secondly, is align to. This function checks if the pointer aligns to a specific boundary given by the align parameter. And thirdly, we have the is empty, which checks if the pointer refers to an empty value. Last one, the length, which returns the length or size of the object referred to by the pointer. So the contract here ensures that the pointer's alignment matches the type it points to, guaranteeing like safe memory access. For the harness, we implemented Kani arbitrary for non-null to generate non-deterministic non-null pointers for testing. This allows us to simulate various scenarios to verify the pointer alignment properties. We also verify invalid alignment situations using Kani-Shapanic to ensure that the system behaves as expected when misaligned pointers are encountered, effectively catching alignment-related issues. The code snippet on the slide demonstrates the implementation of Kani arbitrary to generate a non-null pointer and use assumptions to ensure the pointer is not null before using it.
So above is our detailed technical walkthrough of how we approached the contracts and harnesses for all the APIs that we worked with. And so overall, the results we have is that we wrote overall 48 harnesses and 45 contracts. And remember, we have 48 APIs to start with, and the 3 of them, as Jamie has mentioned, was originally blocked by certain Connie issues. So those do not have contracts yet. And for the ones that we have written, all the Connie checks passes, and we currently have 10 merged PRs, and then there are 3 that are still open. And as of the date of this recording, we're still addressing those comments. And the hope is that they will be merged very soon. And then throughout the process, we identified 6 Connie bugs alongside with AWS, and actually they fixed all of them very quickly. And then in the meantime, we proposed 4 new Connie APIs, and 2 of them has been released by AWS, and right now actively being used in those contracts. And so for the future work, there are mainly 3 things we want to bring attention to. One is to expand the data type. So with the time frame that we're working at here, for many of the harnesses that we are able to use either one or several types, but not able to cover all of the data types that we mentioned in the beginning. So for us and for future contributors, it would be great to include more data types, including primitive data types and also dynamic ones. And the second is to improve the Connie toolchain. So we had a great experience working with the AWS team. And as we're developing, we start to find that there are, for example, additional APIs that will help with the contracts annotation language. And they have been very responsive and continue to discuss with us how to best provide a better user experience. And for the third point is more training resources for the form of verification. So what we found is that, for example, 4 of us are all students, and we had limited experience with this domain. And we found that those, for example, written documentations is really helpful. And also the purpose that we are recording this video right now is to hopefully provide, again, more resources for people who want to tackle this challenge or people who want to go into this specific field to understand what it takes and the design philosophies behind those challenges. And I will encourage everyone to continue adding to those since they're all open source. And then thank you everyone for watching. If you stay with us till the end, we really appreciate it. And that we all want to all invite you to join us in this effort. And here we're leaving some links for you to refer to. And yeah, hope to see you in the future.